Okay, so we're continuing our chapter on temperature and heat. We're looking at heat in this particular case, what exactly heat is. And of course, heat is a form of energy. So basically, the units that we use for it, if we're using SI units, are going to be the joule because that is the unit for energy. Oftentimes, we do use the thermometric calorie, or sometimes we call it the thermochemical calorie or the metric calorie. And that is 4.186 joules. And it's based on the specific heat of water. So basically, if you want to heat 1 gram of water by 1 degree Celsius, it will take 1 calorie or 4.186 joules. We look at the food calories, which are typically on the nutrition fact labels on our food. And we see, oh, okay, calories. Is that the same unit that we have for the metric calorie? And the answer is no. This is actually technically a kilocalorie. We just call it a food calorie for convenience. But in fact, it is technically a kilocalorie, and it's 1,000 times greater than the normal calories we have. So basically, when we're doing this, 1 kilocalorie, okay, is equal to 1,000 regular calories. And we know that, of course, a calorie is equal to about 4.186 joules. So right here, 250 calories. You multiply 250 by 4, okay, so that gets you 1,000, and multiply that by 1,000, that tells you that 250 calories represents about 1 megajoule, or about 1 million joules. So we see that unit of energy from time to time. Again, not the same as a calorie. It's 1,000 times bigger. Let's talk about specific heat. Specific heat is the amount of energy needed to raise the temperature of an object by a certain amount of, by a certain degree. We already said that with water, the specific heat is 4.186 joules for every gram that we want to raise per degree Celsius. But if we look at this right here, it's showing the specific heat for a number of different substances. We see water right here, okay? And that is the amount of energy that we need to raise the substance of 1 kilogram by 1 degree Celsius. So what we notice is that metals are somewhere in the 100s. These are all different metals here. Generally, the rule of thumb is it's not the number of, it's not the mass of the metal, which really determines how much energy that you can store in there. It's really the number of metal atoms that's more proportional to that. It has to do with a lot of the physics of what's going on microscopically and how these move. So basically, we generally see that our lighter metals, like aluminum, are going to have a higher specific heat, whereas the much heavier metals, such as mercury, tungsten's a very heavy metal, and of course lead's a heavy metal, are going to have a lower specific heat because, quite honestly, the atoms themselves have more mass individually. Okay? Going back to water, we know that water is a very high specific heat substance at 4.186. What's strange, however, is it loses its specific heat as it freezes or as it becomes steam. It actually loses about half of its value. You know, there's water down there, there's ice up there. And has a lot to do with how the molecules behave and how many degrees of freedom that they have. But liquid water, looking at this, with the exception of hydrogen, which is just very, very light, it's more about the fact that hydrogen is so incredibly light that it has a high specific heat. Hydrogen gas, there's so few molecules in there, it doesn't really store much energy. But again, water is a great substance to store energy, thermal energy, because of its high specific heat. It's one of the reasons why the New Jersey shore is so popular in the summertime. When it's much warmer inland, the ocean having a large amount of specific heat, it's going to take a lot of energy to get this water to change temperature, okay? Likewise, we can say the water is going to stay relatively cool during a heat wave because even though the air can be very, very warm and air doesn't have a lot of specific heat, it is going to take an incredible amount of energy to change the temperature very much. So the water is going to keep absorbing heat, and on the shoreline, it's going to feel much cooler than it's going to be inland. Likewise, during the wintertime, the ocean will stay much warmer than the surrounding air. It'll give up its heat to the environment. That makes the shore much more moderate during the wintertime. It also makes the shore foggier, okay? During the wintertime, it tends to be less, there's less fair weather there because the vapor coming off of the ocean will condense in the atmosphere. This can be fog, this can be drizzle, and generally, even though it's warmer, we don't get as nice weather down at the shore during the wintertime. So large specific heat of water means that it's a great temperature moderator. The temperature does not change very much at all when we're near the water because of its large specific heat. And of course, this also leads to ocean breezes, which again are really important during a heat wave. When we get that stagnant air and it's just not moving, it's really nice. Talking about inland, we don't have a lot of movement of the air. Along the beach, we're still going to get movement of air in most cases due to convection. And the reason that this happens is that the air will naturally circulate. The warm air on land, it tends to rise, but as it heads out over the ocean, what is going to happen is it's going to eventually come in contact with the ocean and give off its heat. The ocean has a large specific heat, so it can absorb a lot of this energy. That's going to return inland as this nice cool sea breeze during the daytime. Now, during the nighttime, we still get a sea breeze, but it actually reverses. Once again, the ocean having a large specific heat will give off a lot of the heat that is accumulated during the day. It'll rise in the atmosphere due to convection. It'll go inland, and then it will sink as it cools and then be drawn back out to the ocean. So those are the benefits of the ocean, and the reason why the ocean, or at least the shore, becomes very, very popular during the summer, and especially during heat waves, because the ocean will keep the air around it very, very moderate. It's going to absorb a lot of this thermal energy, but also in doing so, is going to generate these sea breezes, which can be very refreshing when the temperatures get very, very high. Now, specific heat is the amount of energy it takes to change the temperature of something. If you heat a substance up, let's do a little graph here. Here's temperature. Here is time. What we notice as we heat something up, it gets warmer, warmer, warmer as we add more and more heat to it. And then what's going to happen is as it begins to change phase, let's say it's boiling or it's melting, its temperature is going to remain constant. What this shows you is that while specific heat tells you how much energy it takes to change the temperature of a particular substance, it is something called latent heat, which will tell you how much energy that substance has to absorb before it can change from a solid to a liquid, or from a liquid to a gas. Or conversely, how much energy it needs to give up to go from a gas to a liquid, or from a liquid to a solid. So specific heat, the amount of energy needed to change the temperature per unit mass. Latent heat, the amount of energy needed to change your phase from one phase to another. And water also has a large amount of latent heat, okay? There are actually two latent heats that we come across. The first is called the latent heat of fusion. The latent heat of fusion is the latent heat that is needed to be absorbed to go from a solid to a liquid. There's also the latent heat of vaporization. That's the amount of heat that we need to put into a substance for it to go from a liquid into a vapor, okay? Here you can actually see the vapor recondensing back into a aerosol liquid. And this happens with a heated pot as the temperature gets closer and closer to boiling. So the great thing about water is, yes, not only does it have a high specific heat, so it takes a lot of energy to change its temperature, the latent heat of water is also very, very large, which means it takes a lot of energy for it to change phase. Now that's very fortunate for us because with the combined specific heat and latent heat of water, what that means is that we can use it to keep systems cool, as is the case for a car. Now this is looking at a car radiator. And of course, what happens here is the hot cooling fluid comes into the radiator and is then blown through these heat exchangers. It's just a large grid with a lot of surface area. And then after it's been cooled, it's returned back to the engine, where it goes to the engine and comes back to pick up some more heat. So really, this allows our engine to stay at a good operating temperature where it can get rid of the heat from the outside by simply dumping it to the outside using this radiator. It actually blows air through these grids, which take the energy from the water. Now, not only does water have a very large specific heat, which means it doesn't take very much water. Usually the water is mixed with some antifreeze, ethylene glycol or propylene glycol. Propylene glycol is used because it's not as toxic, but it's more expensive. And it'll absorb a lot of energy and transfer that energy very efficiently to the outside. The problem is when your engine starts getting into a problem where it can't get rid of enough heat fast enough, the water in the radiator will actually begin to boil. And this will convert the internal heat into latent heat. So if a radiator boils over, it's actually doing its job. It's actually, what it's doing is it's getting rid of the heat as fast as it can because maybe it's too hot outside, or maybe the fan's not working on the radiator, or maybe the engine's just working too hard. But even when the specific heat's not enough, some of the coolant will boil over, and that will give you enough time usually to find a safe place to go and fill up with more radiator fluid or fix your car. By the way, never open a hot radiator. You never open a hot radiator. And the reason for this is it's somewhat under pressure. And what'll happen is if you open up the radiator while it's still hot, you can get scalded. Basically, with all the steam coming out, the steam has a large amount of both specific and latent heat. So if the steam comes in contact with your skin, it will release that heat to your skin. Both the steam will cool down, but it'll also condense, and that can create very, very severe burns. Steam burns are one of the worst. Again, owing to the very large amount of latent heat of steam, 2.6 million joules per kilogram it can really do a lot of damage and create horrific burns. Hurricanes, we've had a lot of hurricanes recently. And one thing to understand is that hurricanes are not just powered by the fact that the ocean is warm. They're also powered by the latent heat of the ocean. So all the heat in the ocean will be transferred into the storm as the water evaporates. And the reason why a storm can grow very rapidly is because when we increase the wind speed, something called Bernoulli's effect lowers the pressure. So the harder we blow the wind in a hurricane, the lower the pressure becomes, and that drops the pressure below the vapor pressure. Well, it doesn't drop below the vapor pressure. It brings the temperature of the water closer to the vapor pressure. The vapor pressure of the atmosphere gets closer to the atmospheric pressure, and more water will enter into the atmosphere, become rain, where it pulls air down with it, rains back down. And essentially, this hurricane becomes something we're going to talk about later on, a heat engine. It transfers heat from the hot reservoir, which of course is the ocean. The warmer the ocean, the more heat it has, and it dumps it into the cold reservoir, which is the upper atmosphere. And in doing so, it does work on the wind, making the wind go faster and faster. Here, of course, is the infamous Hurricane Katrina. And what you're actually seeing are the cloud tops where the cooler air is condensing and coming out of the storm. As it rains back down, this contributes energy to the system, making it more and more powerful. Now, we also use the latent and specific heat of water to cool our bodies down. The humidity from our lungs is almost 100% water vapor, okay? Now, we can see in this upper thing, the water vapor is actually condensing. So when we're breathing, it's in a vapor phase. If it's very cold out, that's not water vapor that we see. That cloud-like material is, again, what we call an aerosol. It's water that is turning back into droplets, and that's why we can see it. But that water vapor, which evaporates in our lungs, takes with it quite a bit of latent heat. So when we breathe, we're actually cooling our bodies. In fact, if you think about dogs can't sweat like we can. Dogs actually will get rid of heat by breathing. And as they're vaporizing this water that's in their lungs, they're actually cooling themselves. They're vaporizing the water that's in their lung. They're vaporizing the water that's in their mouth, on their tongue. And this is really the only efficient means by which they have to cool themselves off in the hot summertime. Again, we're fortunate being able to sweat. We're able to take the water vapor. We're able to take the water. The water will evaporate off the surface of our skin. And as it does so, it takes this energy and dumps it out into the environment and allows our bodies to cool off. When our muscles fire, they produce heat. And in doing so, this excess energy, we've got to get rid of. If we don't, what happens is our body begins to overheat. First thing that we begin to suffer from is heat exhaustion. We might start getting cramps. Heat exhaustion is not typically dangerous in itself, but if it progresses to heat stroke, it can cause permanent damage or even death to our body. So being able to sweat, drinking lots of electrolytes when it's hot out means that we're enabling our body system, our sweat glands, to get rid of the heat very efficiently and dump it out into the environment where our bodies can cool down. Now again, latent heat, the units for latent heat are joules per kilogram. Latent heat and specific heat are not energy, okay? They're a measure of how much energy for a specific thing to happen needs. For instance, specific heat is how many joules per kilogram degree centigrade. Latent heat is how many joules we need to make a phase transition from one phase to another phase, how many kilograms. And just to be specific, latent heat of fusion is usually smaller, okay? Latent heat of fusion is used to talk about the energy whenever we are melting something, okay? We need energy to melt something, so that latent heat we would add to the system, or if we freeze it, we got to take the latent heat away, okay? So heat goes in to melt something, heat comes out if we want to freeze something. The latent heat of vaporization is almost always bigger than the latent heat of fusion, okay? In this case, we are boiling something, okay? We have a pan on the stove, a pot on the stove, and has water in it. We put it on a burner. That burner adds heat to it. And as long as there's water there, that heat will turn some of the liquid water into vapor until all of it's condensed, boiled away. Condensation is the amount of energy we need to go from a vapor back to a liquid. So again, when you look at that photo of that person breathing in very, very cold temperatures, their breath will have to give up a lot of energy. It'll first of all have to cool down and then convert the liquid water, the gaseous water, the vapor in the breath into a liquid. Again, let's take a look at some different latent heats. It's remarkable to look at water. Water is really the interesting thing here. Here is water off right here. And the latent heat of fusion is 333,000 joules per kilogram. It takes a lot of energy to turn water from ice into a liquid. That's why we put ice cubes in our drinks. That ice cube will absorb the heat and keep that drink nice and cool and refreshing as long as the ice cubes are present. Even more extreme, 2.26 million joules of energy are needed to turn water from a liquid at 100 degrees Celsius to a vapor, to boil it away. And again, comparing it to other things, comparing it to a similar substance, ethyl alcohol is just the regular alcohol we find in spirits and drinks. Notice how much lower its latent heats are. Really only the thing with a higher latent heat would be copper in terms of its heat of vaporization. Oh, also aluminum. Aluminum's pretty high too. But those turn into vapors at very, very high temperatures. Okay, let's talk about heat transfer. Heat transfer. There are three methods by which we can get heat to go from one object to another or through an object. The first of all, and the simplest, is conduction. This is where molecules simply bump into their neighbors and transfer the energy to the next molecule. Convection is more complex. Here's where buoyancy causes warmer fluids to rise and cooler fluids to sink. And this sets up usually a convection cell, a convection cycle, where the warm and cold fluids will mix and transfer heat from the warm part of the fluid to the cold part of the fluid. The last really is indirectly transferring heat, and this is thermal radiation. Most thermal radiation is in the infrared part of the spectrum. Only very, very hot objects, we're talking about tens of thousands of degrees, do we really start seeing a lot of the energy being transmitted in both the visible and in the ultraviolet. Okay, so conduction, again, if we think about this, we add energy to one side of a substance over here, okay? That energy causes this to move and this molecule to move and this molecule to move, which is then transferred to the next one, then the next one, then the next one, okay? Not usually a very efficient way to transfer energy. And it takes a long time because each neighbor is transmitting the energy to the next neighbor, and there's a huge number of molecules inside here. It takes a long time to get the heat from the hot end to the cold end. Okay, but some things are able to conduct heat very efficiently because instead of using just vibrations within the material, some materials actually have free electrons, and the electrons can make it from one end to the other, and they can carry the heat with them, okay? These materials are called metals. Metals, because it can conduct electricity, they have a large number of free electrons to move about. They are good thermal conductors, but they're also good electrical conductors because it's the electrons that are transporting both the electricity and the heat. Now, poor conductors tend to be materials where there's not many molecules in them to conduct the energy, and also there are no free electrons that can conduct the electricity. Now, this is getting a little bit higher level than we necessarily want to get, but I'll go over this anyway. We can say that the power, sorry that this is such a crazy looking P right here, the power is equal to the heat divided by the time that the heat takes to transfer. Now, that is dependent on a few things. First of all, what is the material made out of? K is a strong function of the substance. K tends to be hotter or higher for metals, tends to be lower for low density materials. It also depends on the cross-sectional area of the material, okay? The more surface area we have to transmit the heat, the more energy is going to be transferred. Also depends on the thickness of the material, okay? Here it's shown as delta L. On the picture, it's shown as delta X. The thicker the material, the thicker the insulation, the slower the conduction of heat is going to be. Finally, if it's cold outside, the temperature of the inside becomes large compared to the temperature of the outside. We tend to transfer heat faster also. So here's some different materials, and what we can see are materials that are good thermal conductors, materials that are not that good. Good thermal conductors include metals, okay? All the good electrical conductors here are also good thermal conductors. Silver, by no coincidence, is not only the best thermal conductor, it's the best electrical conductor short of superconductors. Why? Because it has the most electrons that are free to move about, and the electrons are the freest. Copper's not bad either. Okay, copper's pretty good. Steel and iron are generally, for metals, they're good conductors in general, but for metals, they're actually poor conductors. Moderate conductors would include materials like ice, stone, concrete, even glass, brick. Water is an okay conductor. But again, these materials have no free electrons, so the only way that they can transport heat from one side to the other is through the vibrations within the materials. Now, the best insulators and the worst conductors include all these materials down here. Snow. You can make a shelter out of snow. Many Inuits will do this when they're on hunting and fishing expeditions. They'll take shelter overnight. They'll build these temporary shelters called igloos. But also mountain climbers will bury into the snow if they get stuck on a mountain and they're unable to descend fast enough. The soil which surrounds your house actually keeps it fairly moderate. You don't insulate your basement as much as you would the rest of the house if you're living in a house, because again, the soil is a pretty good insulator. What's an okay insulator? But the best insulators are made mostly out of air. Fiberglass insulation and air both have very low conductivities. In fact, fiberglass insulation is made mostly out of air and a little bit of fiberglass, and that's why it's comparable to air in terms of its thermal conductivity. The problem with air is we don't want to use air so much for insulation, because air, even though it's a bad thermal conductor, it's great at convection. Air will start moving and convect. So instead, we use fiberglass insulation. Now, another thing we're coming across when we talk about insulation is this concept of R value. R value is a combination between the thickness of the insulation that we're using and its conductivity. The higher the R value, the better the insulation it is. Now, when we go out and we buy insulation, we typically look at, okay, well, what is the R value there? How well is it going to insulate my apartment, or how well is it going to insulate my home? Again, fiberglass insulation is a very common insulation. Oops. The thicker the insulation, the better the R value. As you can see here, at 3.5 inches, R value is roughly around 10. If we double the thickness, we can nearly double the R value. Other materials used for insulation, styrofoam cups are used to insulate your hands from the hot coffee that you're drinking. And there are other things too. Cellulose fiber is oftentimes used. What else? But if we compare it to some other substances, we see where the weak part of insulating some of our structures might be. Obviously, glass. Glass is a poor insulator because it's fairly conductive. Okay. Brick is okay, but not great. Concrete block, even poor R value. And certainly wood doesn't insulate things very well. So in designing a house, we want to first of all look at where our house is located, okay? In warmer areas, we don't have to worry about insulating against the cold as much. Mainly in warmer climates, we're pretty much insulating against the warmth. We want to keep the cold in and keep the heat out. But as we go further and further north, we see that our zones change, requiring more and more R value. So for instance, in Florida, you might only make your ceilings in the attic insulated at R38. In New Jersey, however, you'd have a requirement of R49. So again, fiberglass insulation, this is the Owens Corning fiberglass insulation, which is pink, but it comes in a number of different colors. It's produced by a number of different companies. Again, it is 93% air. The reason why it's such a good insulator is because it's mostly open space. There aren't many molecules in air. Air has about 1,000th of the density of water. And the rest is borosilicate glass, fiberglass. The glass is spun into fibers. And you don't want to get this stuff on you. It makes you very, very itchy. But the insulation is sold in rolls or single pieces known as bats. Great insulating material. But again, in installing this, you want to wear a respirator, and you want to wear gloves, because the fibers can be very, very irritating. Here's a typical diagram showing where insulation would be found in the house. Obviously, the attic. Heat tends to rise, so that's where we want to insulate the most. And we also want to insulate exterior walls. Interior walls, you can insulate, but that would be mainly done for noise control. And of course, insulating the basement, if you want a finished basement, because usually the ground maintains about 50 degrees Fahrenheit temperature. If you want to keep that warm, that should be insulated. Here's a thermal image. This is using thermal radiation to figure out which parts of the house are better insulated than others. Clearly, what we see is the roof's doing pretty well. Blues and greens represent a cooler temperature. The fact that the roof is staying cooler indicates that less heat is coming from the interior, and thus the roof is pretty well insulated. The exterior walls, however, we can see are beginning to show more and more heat transfer. The yellows, indicate that wall's warmer, and because the cold is outside, that heat must be coming from the inside. But by far, the worst offender here are the windows, okay? It is really difficult to insulate windows. In fact, in designing houses, a house designed with a lot of windows, which is nice because it lets in the natural light. It also allows passive solar heating in some cases if it's placed on the south side. The problem is not very good in preventing the heat from going to the outside. So typically, windows will be required to be either 2 panes or multiple panes, maybe triple pane. And what this does is it provides an air gap. It provides a gap in between the glass. Glass is pretty conductive, but the air is not. And they keep it thin enough that you can't really get much convection in there. But the air helps insulate. And again, double pane glass, usually this is code, which means that you have to build most structures with at least 2 panes of glass. But it's not unusual that we would see, triple pane, okay? That we have 1 more pane of glass in addition to this to create an extra barrier against the cold, okay? And of course, that would increase the cost. I don't have triple panes on my house. I think I have double panes, but I actually went to Home Depot and got storm windows and attached them on the outside. So that gives me my extra layer of insulation. But again, the more layers you have, the better off it is. This is a really interesting device. It's been around for a long time. It's called a Thermos. And it works by preventing conduction, convection, and radiation. The first thing that it has is what's called a vacuum. And a vacuum isn't really anything. In fact, a vacuum is the absence of something. So they'll pump out all the air in between these two surfaces. Usually a thermos is either made out of glass or stainless steel, okay? So they'll pump out all the air in between that. So there's nothing to conduct the heat. So no heat can go from the inner surface to the outer surface or the outer surface to the inner surface. The next thing that they'll do is that they'll coat the surfaces or polish the surfaces so they're nice and shiny, okay? If it's glass, they'll vapor deposit aluminum so it's reflective. And by doing this, this prevents radiation from jumping from one surface to the other. Okay, thermal radiation isn't given off very easily by shiny surfaces. In fact, is reflected back. And the last thing is, there's no convection. Okay, without air in between the two surfaces, this remains warm. And even on the outside of some of these, they'll even add styrofoam insulation surrounding this glass or steel container, and then have an insulated top in addition to that. You can keep beverages cold or hot for a very long time, for about a day, because the thermos basically blocks all of these different methods that we can transfer heat. Now again, convection is due to the fact that warm air rises, warm air gets lighter, it becomes buoyant. And what happens here is that the warm air, as it leaves the radiator, pulls in cool air, which then heats up and also rises. And this air will go to the surrounding regions, give up their heat, and then cool down and enter the radiator again. So a radiator uses convection, the fact that warm fluids rise, cool fluids sink, to mix warm air and cool air without actually using fans, okay? Convection is not very, very vigorous, but it's enough to transport heat from the warm part of the room to the cold part of the room. Convection also powers thunderstorms, hurricanes. You know, the warm water vapor tends to rise where it condenses at the top of the cloud, turns back into liquid where it becomes rain and falls back down. So again, your warm water vapor makes its way upward into the cloud. At the top, it cools down, falls down, pulls the air with it. The whole convection process starts over again, okay? It is really convection that drives a lot of the strong winds that we find in many of these storms. Convection is also responsible for our weather. The fact that our weather comes from the west is due to a convection cell called a mid-latitude cell. All right, at our latitude, the mid-latitude cell is dominant. And typically what will happen is at the tropics, the warm air rises near the equator, powers these tropical cells, also known as Hadley cells, and they'll cause the wind to want to go to the south of that location. We also get sinking air below us, and this causes the winds to want to go actually in the opposite direction. I've drawn it in the opposite direction, but actually most of our weather would typically come from the north, but because the Earth spins, the Coriolis effect makes it come from the northwest. So convection powers our wind. It powers the ocean currents. The Gulf Stream will actually send heat to Europe and keep it warmer than it should be. Spans the same latitude as we are, but yet it's a much warmer country than New York and New Jersey. That's because of the Gulf Stream. You can see it in this thermal image right here. It helps, obviously it keeps Florida nice and warm. It keeps the Georgia coast warm and the Carolina coast warm. But as it gets up to Cape Hatteras, notice what it does. Cape Hatteras in North Carolina, it then makes a movement to the east, and we're left without much influence from the Gulf Stream. Actually, we get more of our weather from this, is it the Laurentian current? I can't remember what it is, but a colder current that comes down along Newfoundland and Nova Scotia. But again, convection powers that. It powers plate tectonics, where the heat from the core causes the mantle to rise. The mantle rises, and as it does so, it pulls on the plates and then sinks back down. And again, for conventional purposes, we can talk about convection in our own places where we live. The radiator, again, causes the heat to rise. That goes into the room where it cools down. As it cools, it sinks. And then is pulled back to the radiator where it reheats. And what this ends up doing is it ends up mixing the air so that most of the room is pretty much the same temperature. This constant mixing of warm and cold air keeps us comfortable no matter where we are. Skip some of this. In keeping ourselves warm, we generally want to keep the heat in, prevent the heat from leaving our bodies, but yet not keep the moisture in from when we sweat. And this has led to new technologies for clothing. Obviously, when we cover our bodies with clothing, that prevents the radiation from taking heat away. But with certain type of clothing, this is known as Arctic fleece. What it does is clothing will keep us warm because of the air gaps within the fibers, okay? What clothing does is it holds the warm air to our body. So as long as we can keep the warm air near our body, okay, we will stay warm. The problem is if we do different activities outside, we may produce too much heat. We tend to give off water vapor naturally as we sweat. And if that's held next to our body, it decreases the efficiency of the clothing. If all of a sudden our clothing starts getting wet, we've got a problem here because water is a pretty good conductor. And what that'll do is, as we get wet, it'll take the heat from our body and simply transport it to the outside. So wet clothing is a big no-no, okay? In fact, if you're ever stuck out in the cold environment unintentionally and your clothes get wet, the first thing you need to do is somehow get your clothes dry. So this Arctic fleece, what it does, it allows the water vapor to escape so it doesn't saturate our clothing, doesn't make our clothing wet. At the same time, it prevents heat from escaping from our body by preventing conduction and convection. Okay, thermal radiation. All objects that are warm give off some form of infrared light. Here's an actual thermogram of the human body radiating heat into the surrounding environment, okay? So again, simply by putting clothes on, you're blocking some of this infrared light from escaping to the outside. But we can also use this infrared light to take different measurements such as ear thermometers, allow us to measure the temperature in our ear canal, which gives us a pretty good approximation of what our core temperature is. What it is simply a infrared detector that measures the frequency of the light coming out and the intensity and converts that into a temperature. Now, as things get warmer and warmer, the thermal radiation becomes shorter and shorter in wavelength, and eventually it begins to glow because it's hot. We call this incandescence. Here we can see hot coals, which are incandescent, which are glowing because they're very, very warm. And here we can see a hot tungsten filament in an incandescent light glowing because it gets very, very hot. Now, when objects are hot enough, they glow white hot because instead of just giving some longer wavelengths of light, like you might see down here, the infrared light is shifted, or I should say the radiation is shifted from the infrared to the visible part of the spectrum. And things like our sun are so hot that they actually peak in the visible part of the spectrum around yellow. So again, wavelength, the wavelength of thermal radiation that's given off is actually a function of what the temperature is. We can measure the temperature of things simply by looking at the light that they give off. The universe is cold, so it gives off mostly microwave radiation. Planets tend to be warmer, and they give off infrared. As we go hotter and hotter, two things happen. One, more infrared light is given off, okay? This is a logarithmic scale, which means it goes up by powers of 10. On that vertical axis, the warmer something gets, the more light it gives off. On the other axis, we see wavelength. Wavelength is shorter on the left, it's longer on the right. What tends to happen is warmer objects give off shorter wavelength. Now, we as human beings are somewhere down around, go back to Penn, somewhere down around 300 degrees Kelvin, which means that if you could see the light that we give off, we would see maybe somewhere around here, around 10 microns on the electromagnetic spectrum, okay? Now, that's a very, very small wavelength, but it's still much larger than the visible light that we can see. Heat something up even more, the wavelength will shift to about 1 micron. But it's not until we get in this region right here, around a half a micron, a half a micrometer, or 10 to the minus 6 is a micrometer, that it actually begins to visibly glow, okay? So, looking at this, human beings are right around here. We glow only in the infrared. A tungsten filament is warmer, okay? Or let's say those hot barbecue coals, they're warmer. They glow right around here because at 1,000 degrees Kelvin, most of their energy is in the infrared, okay? You can feel that heat radiating from the hot coals. But a little bit makes it into the visible part of the spectrum. So they glow weakly, this reddish orange color, but again, most of their energy is infrared. Incandescent bulbs, they glow hotter, okay? Maybe around 2,000 degrees Kelvin. All right? But notice they tend to have this warmer color to them. When we look at them, they tend to give off slightly more red light than they do yellow light or green. Come on. and only a little bit of blue. So we tend to say that the incandescent bulbs give off a warmer hue. Okay. Let's go even hotter. Let's go to the temperature of the sun. The sun, if we look at the sky, except for near sunset, it has sort of a yellowish or orangish or reddish hue to it. But the sun at its highest point in the sky looks pretty much white. Okay. It looks white because if we look at the energy given off, okay, it peaks right at the yellow part of the spectrum. That's why we call it a yellow star. It's not really yellow, okay? It's more white than yellow, but it has a little bit of a yellow tinge to it because that's where it peaks. What we know, however, is in addition to giving off visible light that we can see right here, it also gives off infrared light. Walk out into the sunlight and you can feel that infrared light, okay? That nice warm feeling that sunlight gives us. Stay out in the sun too long, and even though the ozone layer of our atmosphere blocks most of it, the UV that does make it through is going to give you a sunburn. So different materials, depending on their temperature, will have different wavelengths that they tend to radiate in. Hot coals, mainly in the infrared, but a little bit of visible light, giving them the reddish orange hue. Tungsten filaments produce this warm, whitish light, but again, not quite as hot as the sun, which glows in the visible. Okay? At even higher temperatures, such as the corona of the sun or a blue star, they will glow mostly in the ultraviolet. And in the most extreme cases, this is a supernova remnant, a star that blew itself up. Some things that are over 1 million degrees are so hot, they're going to actually glow in the X-ray part of the spectrum. So temperature tells us a lot about how things glow. Okay.